Welcome to the second video in a series on developing an HTML5 game from scratch, with no third-party libraries, just you, the markup, and the code, like it was meant to be. In this video, you'll learn about the most common drawing APIs used with Canvas, and you'll also learn about creating animation with Canvas using the Request Animation Frame API. Finally, we'll look at techniques for controlling the frame rate of your animations, as well as some tips for ensuring even and smooth animations. Let's get moving. Drawing on the canvas element is pretty easy, and if you've been following along in this video series, you've already seen a little bit of how it's done. While the Canvas 2D API has a good many members, which you can review at the URL at the bottom of the slide, for the purposes of this video, we're going to focus on three of the most common drawing operations: shapes, bitmaps, and text. Shapes and bitmaps are what we're most likely to use for drawing game elements and characters on the screen, while text is more likely to be used for rendering things like current score and other informational items. The first step in drawing to the canvas element, which you've seen in action if you watched earlier videos in this series, is to get a reference to the canvas element and use its getContext method to get a reference to the 2D drawing context. It's this context object that contains all of the necessary APIs for drawing on the canvas element, so this is something that you'll want to store in your game object for later reference, rather than looking it up each time you want to draw something. For the purposes of this video, we're going to stay at a pretty high level in terms of drawing and cover just the basics to make sure those of you who are new to Canvas don't get lost as we move forward. For a more in-depth video on the HTML5 Canvas API, check out Jeff Procyse's video on the subject at the URL at the bottom of the slide. Squares and rectangles are very easy to draw with Canvas and only require one line of code. The fillRect function creates a filled rectangle, while the strokeRect function creates an outlined rectangle for the given coordinates and size. The fillStyle and strokeStyle properties are used to set the colors, patterns, or gradients for the fill or stroke respectively. These properties also apply when drawing circles and other filled or stroked visual elements. Circles, which are created with the arc method, are a little trickier. Because they're drawn as a path rather than as a primitive object like rectangles, you need to call beginPath before calling the arc function. The arc function takes the x and y center point of the arc, the radius, and the start and end angles in radians. As you can see in the code example, we can use math.pi times 2 to draw a full circle. There's an optional Boolean argument that you can use to draw counterclockwise, otherwise the default is clockwise. A couple of gotchas to know about with the arc method. If you don't draw a full 360-degree circle, you might expect the resulting fill to look like a pie with a slice out of it. But by default, filling an arc that's not a full circle will look like a circle with a flat spot, as you can see in the illustration. To create a circle with a pie-like shape, you'll need to use the line_to function to draw a line back to the origin, and then call the closePath method to finish the line back to the starting point. Calling closePath isn't required, and if you don't call it, a filled arc will still look okay. But if you only outline the arc, part of the outline will end up missing if you don't call closePath. Drawing bitmaps is a very important operation, because for anything beyond very simple games, it's how we'll draw detailed character and background images to the screen, and bitmaps are the basis for sprites, which we'll discuss in a future video. It's best to use bitmap images that are as close to possible to the resolution at which they'll be drawn on the screen. While you can resize smaller bitmaps on the fly, the more you scale them up, the worse they'll tend to look. It's usually better to start with a larger bitmap and scale down than vice versa. The drawImage function you see here takes the image element, the x and y position where you want to draw the image, and optionally the desired width and height to draw the image. If you leave these last two arguments off, the image will be drawn using the native width and height of the image itself. It's important to note that this API assumes that the image already exists and that the source bitmap has been loaded into it. You could do this by including one or more image elements in your markup with the desired bitmap or bitmaps. But often you'll see the elements created dynamically in code, in which case you will need to register for the load event for each of the image elements to ensure that the bitmaps have been loaded before we try to draw them. The implementation seen here is very simple, but if you wanted to get fancy, you could start your game off with a loading screen and use the load handler to update a progress bar each time one of the images loaded, and only start the game once they were all loaded. Unless your game is pretty simple, you'll probably also want to draw some text from time to time, for counters, scorekeeping, and similar things. The fill text and stroke text functions allow you to draw solid and outline text respectively. You can use the font property of the drawing context to set the font size and family, using familiar CSS style syntax. The fill style and related stroke style properties, which also can be used with shapes, allow you to change the color and other aspects of how the item in question will be drawn. Finally, the measure text method can help you with laying out text on the screen. If you pass it the text you want to draw, it will return an object containing the width of the text when drawn. If you're wondering why they pass an object that only has one property, it's probably to provide future extensibility, as the official Canvas specification has several other properties specified for that object. In my testing, neither IE, Chrome, nor Firefox returned anything beyond the width. Be aware that while IE and Chrome return a value rounded to the nearest pixel, Firefox returns a decimal value. In this demo, I'll show you examples of drawing shapes and text on the HTML5 Canvas element. Since we demonstrated drawing a bitmap in the previous video on building a solid foundation, I'd recommend checking out that demo and the accompanying code samples if you want to see the draw image function in action. Let's start by taking a look at a page that draws some shapes onto the canvas. We have a canvas element here, which has a width of 800 pixels by 480 pixels height, and an ID of game canvas. To kick things off, we're using functionality in this drawshapes.js file, which is based on the game JavaScript template that I created in an earlier video. To start things off, we're going to handle the DOM content loaded event, and when that event is fired, we're going to fire off the init function inside of the game object and pass it the ID of the canvas on our page. Let's take a look at the script. In drawshapes.js, the main place where we're going to do our work here is in the draw function. And to see where that's called from, we're going to go down to our init function, which is passed the ID of the canvas, and then it grabs a reference to that canvas and the related drawing context. Then I'm going to call a function called tick, which is going to call the update and draw functions in turn. We'll talk in a little more detail about what all these functions are and the purpose they serve, but let's take a look at draw for now, just to get started. Inside the draw function, I'm going to call a helper library that resizes the canvas to the full size of the screen. Then I'm going to call context fill rect and pass it the x and y coordinates where the top left corner of the rectangle should start and the width and height that I want to draw it at. This is going to draw using the default color. I haven't changed anything about the style of the drawing, so it's going to default to black. Next, I'll call the begin path API because I want to draw a circle, which is a kind of a path. Next, I call context arc and I pass it the x and y coordinates for the center of that arc. Then I tell it the radius of the arc and I give it the beginning and ending angle for the arc in radians. Math.pi times 2 gives us a result in radians that is equivalent to a 360-degree arc or a full circle. Next I call close path, and then I call fill. Fill will fill that arc that I just created with the default color, that is black. If I wanted an outline circle, I could call context.stroke instead. Next, I'm going to draw a partial arc. So just to mix things up, I'm going to change the fill style of the context to red. And if I wanted to set this as RED, use a named color, basically anything that CSS will understand as a color will work here. Again, I'm going to call begin path, I'm going to call arc, and set the center point to 160 by 160, the radius to 25, and the starting angle to 0, the ending angle to math pi times 1.5, which will give me the equivalent of a 270-degree arc. Next, I'm going to call context fill, and we'll see the result here in a moment. Then I'm going to take the same 270-degree arc and mix it up a little bit. So I'm going to draw this at 220 by 220. Again, same radius, same start point, same end point. But this time instead, I'm going to use the line 2 function to draw a line to the center. And then when I call close path, it will complete the line from center to the origin of where I started drawing the arc. That will give me a closed outline. If I didn't call close path, part of that outline would be missing. Then I'll call context stroke, again for an outline in this case. Now let's take a look at what this looks like. So as you can see, we've drawn a rectangle, which has identical sides, so it's actually a square. A circle, both of which use the default black color. Then we're drawing a 270-degree arc, but when we call close path, it actually draws the shortest line possible between the start and end point of that path in order to complete the circle. So what we end up with is kind of a flat-sided circle. To get more of the pie shape that you might expect, we use the same start and end point in radians, but use the line to function to draw a line to the center, and then close path finish that path for us. Now if we go back to Web Matrix, I want to show you a couple of things. One is that if I wanted to, I could change the color of this relatively easily, this rectangle. So if I wanted to change my rectangle, I could say context.fillStyle is equal to, and let's just use a name color, call it blue. Now let's look at this, go back to Internet Explorer and refresh the page. And what I want you to see here is that the square did indeed turn blue, but the next circle also turned blue. So when we change the fill style or similar properties, we're actually changing those for the context as a whole. So if you want those to be just for one particular drawing operation, there's a really easy way to do that. And we can do that, let's jump back into Web Matrix, by saving the drawing context before we make changes. So if I say context.save, what this will do is it'll take the current properties of the context and push them into a stack-like format. So when I save the context, it pushes that onto the stack. There's a restore operation, which if I use that, pulls the last set of properties off the stack and restores them. So I'm going to save the context. I'm going to change the fill style to blue. And then once I've done my drawing operation, I'll call context.restore. If we save that, go back to Internet Explorer and run it again, now you can see that our square is blue, but our next circle is black. So until we change that fill style again, we get the expectation or the expected default color. Likewise, I wanted to show you, if we go back to this last arc and we comment out the call to context.closePath, you'll see if we refresh the page that close path is what's responsible for drawing that last line segment. So we drew an arc around to here, drew a line to the center, but without the closed path, we end up with kind of an odd looking shape. Next, let's look at a page that draws some text to the canvas. The markup here is essentially the same. I've just modified the name of the JavaScript file that contains my game logic, so just wanted to show you that briefly. Let's flip over to that JavaScript file. And again, we're just going to use the draw function here to do our drawing because we're only drawing once. We'll talk about the game loop and such a little bit later on. In this case, I'm going to call context.font, and using that font property, again, I'll use CSS style syntax to set the size of my font and the family of my font to 24 pixel Arial. Then I call the fill text function and pass it the text that I want to draw, in this case, hello world, and the position that I want to draw it at. Then I can call context.strokeText and do the same text in outline form. And again, I'll just change the position here a little bit, make it a little lower. Then maybe I want to make a little bit bigger and more kind of styled text. So I'm going to set the font property to italic, bold, 30 pixel, consolus. So a different family as well. I'm going to change the fill style to red. And then I'm going to stroke the text, which will give me the default stroke style of black. But I'll fill the text with this red color, and in both cases I'm using the same dimensions. So that will give me a red filled text with a black outline. Then I'm going to use this measure text API to see how wide this hello world text would be given the current context properties. And I'll just pass that into an alert box. So we'll see that when we load the page. Let's do that right now. So we can see that we're getting a message via alert that the current hello world text should be about 214 pixels wide, which would help me lay out the page if I wanted to figure out how that would fit with other elements on the page. We can see that by default, we've got our 24 pixel Arial than our outlined and bold and italic and red and all that great stuff. So pretty easy to draw text to the screen. Wikipedia defines animation as the process of creating a continuous motion and shape change illusion by the means of the rapid display of a sequence of static images that minimally differ from each other. The point of animation is to create the illusion of motion in a game, whether that be the motion of a game protagonist or enemy, the background or elements of the background, and so on. If you've ever seen a movie or a cartoon or an animated GIF or a video game, you've seen animation in action. We can think of the canvas element as a kind of a digital flipbook. A flipbook, for those of you who may not have seen or created one, is simply a stack of paper sheets, each with a slightly different image that you flip through rapidly to create the desired animation. With Canvas, we use code to change the images by redrawing shapes, bitmaps, and other visual elements frame by frame, changing their properties with each frame to create the desired illusion. The typical way to do this is using something called a game loop, which we'll discuss next. The game loop serves two basic purposes. First, it allows us to structure our code logically, separating the concerns of updating and drawing into their own functions, which makes it easier to understand what's going on later when we come back to our code. Second, it provides a hook for running the game, with the game loop being called once per frame of the game. There are three basic functions that you'll usually see in any given game. First, the init function is called once at the start of the game, and might also be called each time the game is restarted. It's responsible for setting up all of the necessary prerequisites for the game, loading images and sound files, and initializing internal state variables, and so on. The update function is where you'll modify the values of various game entities, often based on user input. The draw, or sometimes called render, function is responsible for rendering the game's visual entities on screen, based on their current state. Note that as a game becomes more complex, it's often advantageous to write your game entities to be responsible for drawing themselves, and then simply use the draw function to loop through the entities and tell them to draw themselves. We'll discuss this idea more in a future video covering the management of game entities. Input is an important part of any game, but it's not directly involved in the game loop. Why? Because input is event-driven, while the game loop is procedural, which is a kind of a mismatch. So the usual pattern for input is to handle the events for the desired forms of input, such as the on-click, key up, and such events, and modify the internal game state based on the input. Then, on the next call to the game loop, the update function can respond to that input. Don't worry if that seems a little high level. We'll go deeper into input in an upcoming video, since it's a topic that definitely deserves a full video of its own. Until a few short years ago, all animations in JavaScript were based on two JavaScript timer functions, setTimeout and setInterval. Using these was pretty easy. Just call the function and pass it a callback function and a time period in milliseconds after which you want the callback called. SetTimeout would call the function once, and setInterval would call it over and over again until you cleared it. The problem with these functions is that they aren't very efficient at all. They don't know anything about whether the browser tab they're running in is visible. They can't coordinate with other animations and drawing, for example CSS transitions. And for these and other reasons, they tend to be pretty hard on battery life on mobile devices. To solve this problem, the folks at Mozilla came up with the Request Animation Frame API, which allows you to ask the browser to call you back the next time it is ready to render a frame. This allows the browser to coordinate drawing your canvas animations with other rendering operations, and prevents the inefficiency of your code trying to render content that the browser may not be ready to draw. The good news is that as of the time of this video, Request Animation Frame is available in all modern browsers and more than 70% of browsers globally. The bad news is that if you still need to support older browsers such as IE 8 or 9 or iOS Safari prior to version 6 or Android browsers prior to 4.4, you'll either need to use setTimeout setInterval, or better yet, use a polyfill that will allow you to use Request Animation Frame on browsers that support it, while falling back to setTimeout setInterval if needed. You can find out more information on such a polyfill at the URL at the bottom of this slide. Using Request Animation Frame is pretty simple. Just call window.requestAnimationFrame and pass it the name of the function you want called back when the browser is ready to draw the next frame. Typically, this will be the function you use to control your game loop, which will in turn call requestAnimationFrame again, continuing the loop. RequestAnimationFrame targets a frame rate of 60 frames per second, though that frame rate may drop if your rendering operation is especially long or complex, or if the machine where the code is running is lacking in performance. RequestAnimationFrame returns a numeric value as a handle to the current RequestAnimationFrame call. If for some reason you need to cancel the call, you can call the cancelAnimationFrame function and pass it that handle. This is not frequently used, though you might use it to pause your game. In an upcoming demo, I'll show you another way that you can implement pausing logic in your game without needing this API. In this demo, we'll revisit one of the demos from my last video, which shows a very simple animation, and then take a look at another animation that adds a few additional wrinkles. The first demo I want to show you is a demo that I showed at the very end of the video on building a solid foundation for your JavaScript game. It just shows a simple rectangle animated across the screen. Again, we're following the same pattern of having our game script file using the title of the page, simpleanimation.js. We're calling game.init from DOM content loaded. Pretty straightforward. Got our game canvas, etc. Let's switch over to the JavaScript. And what we'll see is we start off by, again, defining our canvas variable, our context variable, and we have this x variable, which we'll see what that's for here momentarily. I've collapsed down some of the functions so we can kind of see it all in one view. Again, the first thing it will do is call init and receive the canvas so we can get the canvas reference and the context reference that we keep throughout the game. Then I'm going to call the game resizer helper and resize the canvas. And then I'm going to call tick, which is going to kind of kick everything off for me. Tick is essentially the manager function that will be called every frame. The tick function is effectively the manager of the game loop in that it will get called from init. And inside the tick function, we're going to call the update and draw functions. And then each frame, we're going to call, again, window.requestAnimationFrame and pass it the tick function so that it will call that back over and over again as long as our game is running. So let's take a look at what happens in the update function. So inside of the update function, all I'm simply doing is taking this x variable and incrementing it by 1. And then I'm going to say if the x variable is greater than the canvas width, then I'm going to set it to a value of -49. You'll see why that is here in a moment. Once update has done its business, then we'll call draw, and I'm going to use a cheat here called canvas width equals canvas width. JSLint, by the way, if you run JSLint on your code, doesn't really like this assignment, but it's a perfectly valid way of clearing the canvas. Then I'm going to call context.fillRect, and for the x position, I want it to be using the x variable. Then for the y position, I'm going to make it the canvas height divided by 2 minus 25, effectively centering the rectangle on the screen. And then again, I'm going to make this a 50 by 50 pixel rectangle. Again, because I have not set any styles on this, this will default to black. So let's take a look at what this does. Very simple demo. We're simply going to animate an item across the screen. Pretty straightforward. Let's take a look at an example that's a little more involved. The markup for the drop start page is pretty much the same as what we've seen before, so we won't bother taking a look at that. When we look at the game JavaScript file, however, dropstart.js, there are some differences from what we saw previously. We've got a couple of extra variables, ball and paused. We're setting pause to false. You'll see why that is in a minute. I'm also going to use object literal notation with ball to create an object with an x variable, a y variable, and an r variable set to 0, 0, and 25, respectively. Inside my init function, I'm going to do the usual canvas and context references, and I'm going to set ball.x equal to canvas.width divided by 2 minus ball.r. Again, essentially centering this ball object on the screen. Then I'll call tick to kick off my game loop. Inside the tick function, as usual, we'll call update and draw, but this time we have an if statement that checks the value of the paused variable. If it's not true, then we're going to call window.requestAnimationFrame and pass it, again, the name of the tick function that we want called back. Essentially what this allows me to do is either manually or through user input means set the value of this paused variable to pause our game. Inside of the update function, I'm going to check whether the position of the ball in the y direction plus its radius is less than or equal to the canvas height. If it is, then I'm going to increment the value of the y position of the ball. Otherwise, I'm going to set the paused variable to true. This will allow me to stop my ball from going through the bottom of the screen. Inside the draw function, I'm going to call the clearRect API. This is a different way than we showed before of clearing the canvas. So this function takes the beginning and ending coordinates of a rectangle that I want to clear on the canvas. In this case, since I'm starting at 0, 0 and ending at 800 by 480, I'm going to clear the entire canvas. Then I can call begin path, arc, and again I'm going to draw a full 360-degree circle, and I pass in the x and y position of the ball object as well as the r variable of the ball object. So this allows me to use properties of a particular entity to draw that entity on the screen. Then I'll call close path and fill. So what we should get is a black circle. Now, each time we draw that frame, or each time we update our information and draw the frame, remember we're incrementing the y position of that ball. So the ball should drop from the top of the screen to the bottom. Let's take a look and see if it does. And indeed, we see that the ball is dropping at a consistent rate from the top to the bottom of the screen, and when it reaches the bottom, it stops. The game is paused. That's a good starting point, but obviously that's not the most exciting ball drop you've ever seen. So we'll actually take a look in a future video at how to use physics and math to make things look a little more realistic in our animations. In game development, as in just about everything else, there's no such thing as a free lunch. Using Request Animation Frame will ideally give us smooth animations with a frame rate at or near 60 frames per second. But every frame that we render costs us in terms of processing cycles. It may well be, in some cases, that 30 frames per second would be adequate for our needs. Given that the Request Animation Frame API does not provide a means for controlling frame rate directly, one technique that you can use is to wrap your Request Animation Frame call within a call to set timeout, and make the timeout's interval such that it results in the desired frame rate. You'll still get all the advantages of Request Animation Frame, but with fewer frames being rendered overall. Note that the code shown here is using 1000 divided by 30 to target approximately 30 frames per second. In a real game, I'd usually replace the 30 in that equation with a variable that is set to that value, so that if desired, the frame rate could be updated more cleanly and easily. The Request Animation Frame API has another hidden bonus. When it calls the callback function, it passes a high-resolution timestamp that, according to the spec, should represent the amount of time that has passed since the page was navigated to. By storing this value and then subtracting it from subsequent timestamps, you can get the elapsed time for each frame and adjust your animations accordingly. This will ensure that your animated shapes and characters travel a consistent distance over time, even in the event of the frame rate dropping for some reason. Without the use of time-based animation, movement of on-screen elements would vary based on the frame rate. For example, if we move a circle across the screen at 10 pixels per frame, it would end up moving much faster at 60 frames per second than if the system was taxed and could only manage 30 frames per second, which is a possibility when using Request Animation Frame. To solve this, time-based animation moves on-screen items based on a concept of pixels per second and uses the time delta between the previous frame and the current frame to calculate how far to move the item. While this doesn't prevent the occasional dropped frame hiccup, it will allow your animations to be more consistent across devices and frame rates. It's also important to note that the timestamp that is passed to the callback by Request Animation Frame is different from what was passed in earlier versions of this API. Originally, the value passed was the equivalent of calling the getDate function in JavaScript. Another commonly used technique to improve the smoothness and performance of animations is called double buffering. In this technique, you draw game elements onto a second hidden canvas, and then copy those elements onto the visible canvas as bitmaps. This technique works best when the hidden canvas is sized to tightly fit the size of the game element being drawn, which minimizes the number of pixels being cleared and drawn in each frame. though you can still gain some performance benefit by simply creating a second canvas identical to the first and drawing your elements to it, then copying to the visible canvas. In this demo, we'll take a look at the use of the set timeout technique to throttle our simple ball drop animation, as well as using time-based animation to ensure that our animation looks roughly the same regardless of what happens to the frame rate. This example is based on our previous demo in which we make a ball drop from the top of the screen to the bottom. In this case, what I want to do is demonstrate both throttling of the frame rate for the animation as well as using time-based animation to ensure that the ball will consistently fall the same distance over the same period of time regardless of frame rate. So in our JavaScript file, again, we've got our canvas and context. We've added a variable for the frames per second, which we've defaulted to 60, and then a couple of variables for dealing with time and time deltas. So we're going to look at the last timestamp and the time delta. We've updated our ball object to include a speed variable, which we're going to set to 100, which is the number of pixels per second that we're going to move the ball from the top of the screen to the bottom. In our init function, we're again going to set the X position of the ball to essentially center it on the screen and call tick to kick off everything else. Inside of tick, we're going to check the last timestamp variable. If the last timestamp variable has a value, remember in JavaScript there are truthy and falsy values, so if a variable has a value, it can evaluate to true. So this will evaluate to true if we've set a value for this. If this currently doesn't have a value, it will evaluate as false, in which case we'll set the last timestamp to the time, and we'll set the time delta to be 1 divided by 1000. If last timestamp does have a value, then we're going to get this time delta, and we're going to set it to the time that we receive from request animation frame minus the last timestamp, and divide that by 1000 to get the number of seconds since the last frame. Then we're going to call the update function and pass it that time delta variable. So inside of update, we're going to receive the delta. We're going to again check to make sure that the ball has not reached the bottom of the screen. If it has not yet reached the bottom of the screen, in this case, we're going to increment the y variable on the ball object with the value from the ball speed times the delta. So we're going to take that 100 pixels a second times the number of seconds since the last frame and increment by that much. That ensures that no matter if we drop frames, no matter if our frame rate is 30, 15, 60, the ball will move at the same rate regardless of that frame rate. And then again, if the ball reaches the bottom of the screen, we'll set paused equal to true. Then once we've done the update, we call draw. And again, we're going to use our paused variable to make sure that we only call request animation frame if the game is not paused. I've also added that set timeout technique to restrict our frame rate or throttle our frame rate based on the frames per second variable. So let's look at the draw function, which is doing essentially the same thing as we did before. Didn't need any changes to that at all. So let's see this in action. So we can see our ball is dropping a little bit faster than before, just a slight difference in terms of the value. Now if we go back into Web Matrix and modify the frame rate to 30 frames per second, and then refresh the page, what we'll see here is our animation's a little more choppy because we're having to move more pixels per frame, but our distance that we travel in that time frame is exactly the same as it was before. And you'll see if I switch back here and drop this even further, that if I were to do a 15 frames per second frame rate, our animation starts to get pretty jaggedy. But again, we reach the bottom from the top in the same amount of time. So again, the time-based animation allows us to control how far our characters move within a given amount of time regardless of frame rate, and the set timeout technique allows us to throttle our animation to a desired frame rate. To wrap things up, here are a few additional resources you may find useful. Bear in mind that some of the tutorials and posts are a couple of years old, so they won't always show all of the most up-to-date techniques, such as the use of the Request Animation Frame API. That being said, they're still pretty useful in terms of gaining a deeper understanding of some of the underlying concepts relating to drawing and animation with Canvas. In this video, you saw how easy it is to draw shapes, text, and more on the screen using the HTML5 Canvas API. You learned how the game loop helps us organize the code in our game, and how you can use the Request Animation Frame API to make sure that the game loop is called when the browser is ready to render. And finally, you learned about techniques like time-based animation and double buffering that can improve the results you get with Canvas, even when your frame rate takes a hit. I hope you've enjoyed watching, and I invite you to come back for future videos in this series. Thanks for watching.